Hello everyone. In today's session we'll be discussing about the instruction BLX. But before we discuss anything with respect to this, one thing you should know is this particular instruction will only work in 5th version of ARM ISA or above that. And so if you try to use this particular instruction in LPC 2148, you will get unknown opcode or unknown target errors. Okay, but now let us just learn more about this particular instruction. Very first thing is, what exactly is BLX? It is branch with link and exchange. Previously we learned about BL and BX, that is branch with link and branch and exchange. So this particular instruction contains features of both BL and BX that we will discuss later. Okay, before that we'll see how exactly you write this particular instruction, that is BLX followed by any conditional code if required, and then you can either have a label written here or you could just have a register. Okay, so both these formats are allowed. Now since I have already told it has features of BL and BX, let's see what are those features. What happens in case of BL? We use BL in order to call a particular subroutine, correct? When you write BL followed by the name of a subroutine, what will happen? Control jumps there. Okay, and along with that link register is also updated. What do you mean by control jumps there, or jump happens to that particular address? PC is updated with the address of that particular subroutine. Okay, and along with that, what happens to link register? Link register points to the very next instruction which is written after this BL instruction. Okay, so same thing happens even in the case of BLX. If you write any instruction like BLX followed by the label or BLX followed by a register, okay, in both the case what should happen? Jump should happen to whatever address is provided either by the register in this case or by the label, because we already know label always marks certain memory location. So in both the case, whatever address is provided, that is updated in the PC, and the address of the very next instruction is stored in the link register. Now these were the features of BL that we see even in BLX. What difference do you see between BL and BLX? That is the feature that we have observed in BX. What is it? The switching part. We know whenever we write BX followed by any register, one thing we always noted is, if this is your register, okay, total 32 bits are there, 0 to 31, like this. If this is your register, whenever the return is carried out, okay, after executing the subroutine using this particular instruction, the CPU checks the LSB bit, and based on that it will switch the execution state to either ARM mode or thumb mode. That is, if the last bit of the register content was 0, then it would switch back to ARM mode. If it was 1, then it would switch back to thumb mode. Same feature is seen here. Now if we check this particular case where there is something called BLX followed by some register content. So this register's last bit, okay, now this is 31, this is 0. Okay, the last bit of this particular register, it is checked. If it is 1, then it expects that the subroutine is made up of thumb instruction, and if it is 0, it means the subroutine is also made up of ARM instructions. That is, in short, BLX, along with performing the two tasks that we expect, that is updating PC and LR, it will also perform switching between ARM to thumb or thumb to ARM. Okay, that differentiates it from the instruction BL. Let us first understand something. Whenever you write ARM and thumb code combined together, okay, in a particular file, always remember that you have to use an assembler directive called thumb. before you start writing the relevant thumb code. This is the command through which the assembler understands that the next set of lines are actually thumb instructions. Okay, so this is the very important step that you should remember, because as soon as this is determined, if there is a register filled with some address, okay, which points to thumb section, okay, assembler adds 1 to the last part of address, that is assembler adds 1 to the LSB of the address. Fine, because of which CPU will understand that the subroutine actually belongs to thumb instruction set, because of which its execution state is changed from ARM to thumb. Okay, what does that mean? If you want to check, you can see the CPSR T bit, it will have changed from 0 to 1 as soon as this particular instruction is encountered, and this happens only if thumb is written before the subroutine. And one more thing we should notice here is it doesn't jump to the location address plus 1, it will jump to the determined address only, and the last bit is updated only for the CPU to know to which particular execution state it should jump to, that is whether it should jump to ARM or thumb. In short, CPU is the one which checks the LSB of the target, and then it sets the T bit of CPSR accordingly. Fine, and then after that it will clear the LSB, it will make it 0, doesn't matter if it's initially 0 or 1 as set by the assembler. Once T bit of a CPSR is set, CPU makes it 0, so that the appropriate address is updated here in PC and continues execution in the correct instruction set. One thing you should remember here is all this LSB checking concept that we discussed now only applies to BLX followed by register. Okay, because in the case of BLX followed by label, the target address is encoded in the instruction itself. That is because the assembler and linker already knows at build or link time whether the label is in thumb or not. Okay, so the instruction encoding itself implies the state change, that is whether the CPU should jump to thumb or not is already determined. Okay, and there is no LSB checking additionally required by the CPU. If we ignore the part of LSB being set or reset and determining whether ARM to thumb or thumb to ARM switching is required or not based on the LSB bit, all the next steps like setting the T bit, updating PC or link register remain same in the case of both BLX followed by label and BLX followed by register.